When it comes to graphing linear inequalities in two variables, which is the focus of this video, you do have to merge two things. You're basically merging this idea of those linear inequalities in one variable that we already learned with this idea of equations in two variables that we recently learned. So you're kind of merging these two things. So these graphs are a little more involved than just a linear equation in two variables, and it's a bit more involved than just a linear inequality in one variable. So remember, we're merging two big things here. Okay, so definition, the graph of a linear inequality in two variables is the set of all points whose, I've got a picture in the way, whose coordinates satisfy the inequality. So what's going to happen here is, remember, with those inequalities in one variable that we already talked about, we had, remember I showed you this in the previous video, but we could have something like x is less than 6. We would draw just a number line. We would indicate where the end point was. We would use a rounded bracket to tell the reader, hey, we can't include exactly 6, but everything less than that is good. We also had the situation where we had x is greater than or equal to -3. Again, you would draw a number line. You would locate your boundary point or your end point, which was -3. You would use a square bracket to indicate to the reader that you could include the 3 or the -3, and then you would shade to the right to include all of those points too. So we have to take that idea but translate it into this two-dimensional space where we graph linear inequalities and now linear equations and now inequalities in two variables. Okay, so we have to talk about that. So now, instead of having this situation that I've drawn out, we're going to have something like this where we're drawing in that two-dimensional space. Okay, so envision a line, just any old line. Well, what this line does is it breaks this Cartesian plane into two regions called half planes. So this line, you have the half plane above the line, and then you have the half plane below the line. The line itself is like the end point. I call it a boundary line, okay? So it's kind of like over here in this world where we had the linear inequalities in one variable, we had an end point. Well, now we treat the actual line itself as the end point. You either include the points on the line or not, and then you include one of the two half planes, okay? So just so you know, a half plane is a set of all points on one side of the line, okay? So we've talked about what a half plane looks like. We've drawn it out here. Next, we have the graph will consist of one half plane and then may or may not include the points on the line. Remember, the line is like our boundary or our end point, okay? You either include those points or not, and then you include one of the two half planes, okay? So that's kind of how we transfer that world from linear inequalities in one variable with that world of any linear equations in two variables. We got to kind of make those two things come together and marry. All right, so steps to graph a linear inequality in two variables. We're right here now. So you solve the inequality for y. I think that is just, to me, it's just the easiest way to do this. It's the way where you have the fewest mistakes, okay? So it's my preference that you solve the inequality for y and then plot the y-intercept and apply the slope. So starting off, this is going to feel very much like graphing an equation in two variables. You solve for y, you figure out what the y-intercept is, you plot it, you apply your slope, and then you tap the brakes, okay? Because the next step is where things get a little different. So you do want to connect the points with a line, but remember, we either include that boundary line or not. And so we have to do something to indicate to the reader which of those things is going to happen. So you're going to connect your points with a solid line if you use the or equals to inequalities. So if you have a less than or equal or a greater than or equal inequality, you're going to connect those points with a solid line because those points mean you include the points on the physical line, okay? Now, if we had not a dashed line, if we have a strict inequality, a strictly less than or a strictly greater than inequality symbol, we would use a dashed or a dotted line. That tells the reader that we do not include the points on the line in our solution set. So the dashed line is kind of like what we have here, and the dotted line or the solid line is what we have here, okay? So the solid line is kind of like including that end point with the square bracket or the closed circle. The dotted or the dashed line is like the rounded bracket or the open circle, which says don't include that end point, okay? So we have to solve for y, plot the y-intercept, apply the slope, tap the brakes, think about, do I include the points on the line or not? use a solid line or a dotted line, and then you have to choose the half plane that is going to be part of your solution set. And ultimately what we do is we test a point, okay? You want to test a point that is clearly not on the line. It has to be clearly above or below the line. So you test that point, you plug it into the original inequality. If when you do that, you get a true statement, that tells you that ordered pair is part of the solution set. Therefore, that half plane that the point lives in would be part of the solution, so you would shade it. If you were to plug in a point and get a false statement, that tells you that ordered pair is not part of the solution set. And the half plane that contains that ordered pair would not be part of the solution set, so you would shade the other side, okay? So we got a good bit going on here. I think it's easiest to understand with an example, okay? So let's look at some examples here. So example 2 says graph each linear inequality. I'm going to start right off the bat by solving for y, okay? So I'm going to go over here to the side. We have 5y plus 10x is less than 15. Well, I want to isolate the 5y. The issue is the plus 10x. So I'm going to start by subtracting 10x from both sides. Don't be alarmed by the inequality. We'll deal with that as we go. So on the left, my 10x has become 0. I'm left with 5y is less than negative 10x plus 15. Next, I would want to isolate the y by dividing by 5. We need to undo the multiplication of 5 and y, so I divide everything by 5. Here's an area that you need to be very, very careful. If the coefficient on y is negative, we would end up dividing the entire inequality by a negative. And remember from the previous chapter, that would mean we would have to reverse the inequality symbol. Here, we're dividing everything by a positive. We don't have to worry about that, but kind of keep it here because it will come up at some point. So we're going to divide everything by 5. So this tells me that I have y is less than negative 2x. So negative 10x divided by 5 is negative 2. And then 15 divided by 5 is 3. So this inequality, it's the same as what I started with. It's just in a new format. And it's in a format that's very useful because I get my slope and my y-intercept for free. So my slope here is negative 2. My y-intercept is 3. Let's go ahead and talk about what we think is going to happen here. So we have a strict inequality. This means that we have this boundary line, and the boundary line cannot be included in the solution. It's kind of like that idea of an open circle or a rounded bracket. Because we have the strict less than inequality, we don't have the or equals to, we're definitely going to connect with a dotted line. Now, as long as you solve for y, it tells you which half plane you're going to shade. This says that y is less than. So think shade below, but we will definitely test a point in just a minute. Okay, so let's go ahead and start. We want to plot our y-intercept and apply our slope. Okay, so we're going to plot the y-intercept of 3. So remember, that's the ordered pair 0, 3. So I would start at the origin. I would not go left or right. I would just go up 3. From there, I want to apply my slope. Now, my slope is 2, but we always like to have our slope in fraction form, so I could think of that as negative 2 over 1. So from my y-intercept, I could drop down 1, 2, and then go to the right 1. I could do that again. I could go down 1, 2 to the left or to the right 1. Or remember, we can reverse both of those steps. Instead of going down, I could go up. Instead of going right, I could go to the left. So I could go up 2 to the left 1. All right, make sure you have at least 2 points, and then you want to connect them. And remember, don't just connect them willy-nilly. We have to remember, do I connect with a solid line or a dotted line? In this case, we need to connect with a dotted line. Now, I suspect we're going to be shading below this line. That means shading the bottom side of the line, okay? So what we want to do is test a point, all right? I like to test the origin. It's just easiest if you test the origin. So I'm going to test 0, 0. Now, if your line goes through the origin, you have to test something else. But for this one, we can test the origin. So I'm going to take my original inequality. Anywhere I see a y, I'm going to put a 0. Anywhere I see an x, I'm going to put a 0. And I need to know if that is less than 15. Well, 5 times 0 is 0. 10 times 0 is also 0. 0 plus 0 is just 0. So we're dealing with 0 is less than 15. Is that true? Yes, this is true. So that tells me 0, 0, which is right here, is part of the solution set. That tells me I must shade the half plane that contains my test point. So I would just gently shade, and that's the solution here. So you have this boundary line. You do not include the points on the line. You include everything underneath that. Okay, let's look at part B. So for part B, we have 3x minus 2y is less than or equal to 8. So 3x minus 2y is less than or equal to 8. We want to isolate the negative 2y, so I'm going to move the 3x. I move it with subtraction. That leaves me, the 3x's just become 0, so that leaves me with negative 2y is less than or equal to negative 3x plus 8. All right. I need to undo the multiplication of negative 2 and y, so I'm going to divide everything by negative 2, and hopefully that mathematician in you was like, whoa, wait a minute, something weird is happening. Yes, something weird is happening. We're dividing an entire inequality by a negative. When you divide an entire inequality by a negative, you have complete sign changes, and to compensate for those sign changes, you, the mathematician, has to reverse the direction of the inequality symbol. So we are going to divide all three terms by negative 2. Looking at the first term, it started out as a negative, but when I divide it by negative 2, I just get positive y. The middle term started out negative, but when I take negative 3 and divide it by negative 2, I get positive 3 halves x. And then the last term was positive, but when I take positive 8 and divide it by negative 2, I get negative 4. So we went from negative to positive, negative to positive, positive to negative. All the signs changed. To compensate for that, we have to reverse the direction of the inequality symbol. So this is now going to be y is greater than or equal to 3 halves x minus 4. Okay, make sure you switch your inequality symbol. Now the slope here is 3 halves. The y-intercept is negative 4, or remember, it could be 0, negative 4, the ordered pair. Okay, now because we do not have a strict inequality, we have one of those or equals to inequalities. That tells me that I can include the points on my boundary line. So I'm going to connect with a solid line. And because I have y is greater than, I suspect I'm going to shade above the line or on top of the line. So as long as you solve for y, the inequality tells you where you're going to shade. If you have a greater than, you're going to shade on top of the line. If you have y is less than, you're going to shade below the line. But we always test a point just to be safe, okay? So let's go ahead and get our line, and then we'll test a point. So I want to plot my y-intercept, which is right here. So my y-intercept is negative 4. So at the origin, I do not go left or right, but I do go down 4. And then from there, I want to apply my slope. Now, my slope is positive 3 over 2. So that tells me to go up 3 to the right 2. So I go up 1, 2, 3 to the right 2. Up 1, 2, 3 to the right 2. I could also, instead of going up 3 and to the right 2, I could go down 3, but then I have to go to the left 2. Either way, I'm on a line. Double check before you connect. Do we want a solid line or a dotted line? In this case, we do want a solid line. We have that greater than or equals to. That means the points on the line are part of the solution set, and we tell the reader that by using a solid line here. Now, I always test the origin simply because the origin is easy to plug into inequalities. The only time you don't test an origin as your test point is if the line goes through the origin. The line doesn't go through the origin, so I'm going to test 0, 0. Let's see what happens. So I'm going to take my original inequality. Anywhere I see an x, I'm going to plug in a 0. Anywhere I see a y, I'm going to plug in a 0, and then we're going to see if it's true or false. Well, 3 times 0 is 0. 2 times 0 is 0. 0 minus 2 is 0. So we have 0 is less than or equal to 8, and that is definitely true. 0 is less than 8, so it satisfies this here. So because this gave us a true statement that tells me 0, 0, the solution is part of the shaded region, or the solution. The test point is part of the solution, so we need to shade the half plane that contains the test point. The test point is here. So we want to shade the half plane that is above or on top of the line. And that's what we suspected from the start, is that we would be shading on top of the line. Okay, so that's quite a bit, but I do want to show you a few more examples. So this video is going to be, a bit longer. Whoops. So here we have example 3. So we're going to graph each linear inequality, and these are going to be more of the special cases. So let's look at part A. So again, the directions just say graph each linear inequality. In part A, we have y is less than or equal to 1/4 x. Now, what I hope you notice is we have a y, we have an x, we don't have a constant. And this has come up for us before. We've seen situations where we had y is equal to just an x term, but we didn't have anything added or subtracted to that. So we had to remember there's secretly a plus 0 here. The same thing is true for inequalities, okay? So what's going to happen is this goes through the origin. All right. So my y-intercept is just 0, 0. My slope is 1/4. We can go ahead and get started. Okay. So I'm going to plot the y-intercept, which is 0. And then I'm going to apply my slope. So initially I have +1, which tells me to go up 1. And then I have +4, which tells me to go to the right 4. So I go up 1, to the right 1, 2, 3, 4. I could do that again, up 1, and then to the right 1, 2, 3, 4. I could also, instead of going up, I could go down. And instead of going right, I could go left. So I could go down 1 and to the left 4. Either way, we're on a line. Now, always at this point, be careful, double check. Should we connect with a solid line or a dotted line? In this case, we want a solid line. We have y is less than or equal to this 1/4 x. So we do want to connect these with a solid line that tells the reader to include the points on the physical line. And then we need to test a point. The issue here is we go through the origin. And since we're going through the origin, we can't test that point. Okay, we have to test some other point. So I usually test an intercept, either an x or a y intercept, just because they're, they have at least one value that's 0. So let's see what we get here. Let's test. I think I want to test x equals 8. Okay, so if I look at this, x equals 8 is 1, 2, 3, 4, 5, 6, 7, 8. X equals 8 would be right there. So that would be the intercept. I should say the x-intercept. So we're looking at the point 8, 0. So we're going to test 8, 0. So I'm going to take the original inequality. Anywhere I see a y, I'm going to plug in a 0. Anywhere I see an x, I'm going to plug in an 8. So then I have 0 is less than or equal to 1/4 times 8. Well, 1/4 times 8 is 2. So is that true? Yes, that is absolutely true. 0 is less than or equal to 2. So the ordered pair that we tested was the point 8, 0. I've got that plotted here on the x-axis. It gave us a true statement when we plugged it in. So it tells me that is part of the solution. So I want to shade the half plane that contains that point. Okay, now the last two examples we're going to look at here are horizontal and vertical lines, and they just don't require the same amount of work, but you do have to understand what's going on. Okay, so let's look at part B. So part B, we have x is greater than 3. We know that when we're in this world of equations or inequalities in two variables, if you're missing one of the variables, that means you're either horizontal or you're vertical. So the variable we're missing is y. That means we cannot touch the y-axis. But we do have to touch the x-axis. And the only way for that to happen is if we are parallel to the y-axis, which means this is a vertical line. And we know that this right here is the x-intercept. So if you ever have a situation where you're missing one of the two variables, solve for the variable you do have. Well, we didn't have to do any work here. We just had x is greater than 3. So we know that once we solve for whatever variable we do have, that becomes its intercept. So we need to find 3 on the x-axis. So 1, 2, 3. And then we have to decide, do we use a dotted or a solid vertical line? Well, here we have x is strictly greater than 3. So we're going to do a vertical line through 3 on the x-axis. And then when we're doing the greater than or less than, here it's going to be left or right. So to the left of this line would be less than, to the right of this line would be greater than. So we want to shade the half plane that is to the right of this vertical line. Now for part C, we're missing the x. So that means we can't touch the x-axis, but we have to go through the y-axis. That makes us horizontal. Okay, so since this has already been solved for y, we know this is the y-intercept. So I want to find -2 on the y-axis, and then we ask ourselves, is this going to be a solid line or a dotted line? Well, we do not have the or equals to component, so this is definitely going to be a dotted line. That tells the reader that the points on the line do not count. And we want to be less than this line. So with a horizontal line, you shade on top or below. In this case, we want to shade below. So that is graphing linear inequalities in two variables. It is kind of time consuming. I know this video was long. Hopefully you stuck with it. Just make sure you know how to deal with regular old inequalities and then these kind of special cases, the situation where you go through the origin and then vertical and horizontal lines.